So I wanted to start off today with the reflection paper. See what, just to kind of have a little discussion on reflections. As you went through that in a little more detail, if you had any questions, concerns that highlighted, or if it made it better or worse.
It wasn't terrible. I mean, nothing that when we went through it the first time that I did have a concern about it.
Okay.
It's just getting it done in a timely manner and finding a topic that's going to provide data and sources.
Yeah. Yeah, that's why we'll try to get started on that here pretty short too. Luke, what about you?
But when I wrote mine, I kind of have a firm idea of what I want to write about. My concern is that I'm not going to be able to find enough relevant data to like the specific point that I'm trying to make. Yeah, I also hate ABA. So the whole format thing also.
Yeah, formatting is always a bear, no matter what. All right, so let's kind of press on with the next apps. And let's see, I'm going to open. If you guys do the, let's go ahead and just open up the integrated to regression. Integrated integrated introduction to regression. That is, oops, that is this app 9.
Are all the due on Thursday?
Yes.
Well, the one, two we worked on yesterday would do today. Right?
Yeah, before class today. Yeah.
Oh, you did for class?
Yes.
Oh, that's a problem.
Okay, so today's kind of a big day. We'll get into the other details of it. So, so yesterday where we left off with running our first regression, getting this detail here, and we ran the two variables, right? So do you guys got any questions here? R squared went up. If we're going to learn that once you add a variable to a regression, R squared is always going to go up. But sometimes it won't go up by very much, but it'll always go up. So today, you see. All right.
JC's like, I'm on it.
So this one has a lot on it. So let's kind of start in this main goals here. So this worksheet has 4 main goals to understand T-stats, J1 through R25. So go ahead and find J1 through R25 on your sheet. J1 through R25.
We're just skipping 7 and 8.
Skipping 7 and 8. It's all, we're doing 7 and 8 right now. So I pull open the integrated one. This is the rest of the sheets. They're all actually here. So here's the first stuff we did. But the author kind of doesn't want to overwhelm you with all of this all at one time. So that's why we're working. But now we're ready, I think, to take it on. All right, so calculating, this is calculating t-statistics relation to a critical t value to learn a mistake-free estimation method and to understand confidence intervals, J26 through R47. Go ahead and check out J26 through R47. J26 through R47, so that's this part 3. So we got these 3 parts here: understanding key statistics, understanding, number 2, the mistake-free way. So it's all highlighted in yellow, the mistake-free way. And then he backs over to here with number 3, understanding confidence intervals. And then understanding the difference between magnitude and significance. Okay, are you ready?
Oh. Yeah.
So, go to understanding t-statistics. Part A, the coefficient is the best guess as to the value of the intercept or slope. What does coefficient mean? In our layouts,
I grab my markers and we did it.
what is a coefficient versus a variable? Tell me what a variable is versus a coefficient. It's good to have that terminology. Let's start with a variable. That one should be easy. We can look at this. Here's, you can look at this sheet if you want. What's a variable in this particular pizza, college town pizza data? What?
Price of slice.
Price of a slice. So the price of a slice is the variable. Tuition, price of a soft drink. So these are all independent variables, but you'll also hear them referred to some other terms. So they're kind of external to the model. So we sometimes call the quantity the choice variable. And then we'll might be referred to some other stuff too, but we don't need to. So what's a coefficient then? Okay, good. So it tells you the sensitivity. So if we go back to our equation, so we sometimes, maybe you've seen this already, the left-hand side of the equal sign is the dependent variable, which, as we've learned in Excel, is going to be the y variable, right? Quantity of slices is equal to A plus B1 price of slice plus B2 price of soft drink. I'll stop there. So what the coefficient is this part, right? That's the coefficient. And these are the coefficients. And these are the coefficients. So as JC just said, the coefficient is the thing that's showing the responsiveness of the variable to the dependent variable, the relationship. So if we had a slope term or whatever. Okay, so it's good to have that. So the coefficient, back to A here, is the best guess as to the value of the intercept or the slope. So the best guess, how did we come up with the best guess yesterday? What did the computer do to come up with the best guess? Run the regression, and what did the regression do?
Squares.
The least squares of this little cluster, right? So we'd like to think that the demand curve is downward sloping, or there's some sort of connection between all of these variables. And so by fitting a line so that, and we do it a line, by the way, just because we're trying to force it to look like that. It doesn't have to be. It can be a curve, as we did with the elasticity chapter. So there's different functional forms, but we're kind of forcing a line into here, and the best fit line, the technique that the computer runs through with regression, is to take the distance between the fitted line. I think this one is found that in the bag. Is to take the sum of the least squares. So from this picture, what was the residual? What was the residual from this picture we did yesterday? How would you describe what a residual is? We generated the residual plot. Okay, what about it? So the data point, that is the residual?
Or the distance from, the vertical distance from the data point to the square regression.
Good, okay, so that is the residual. That vertical distance is the residual. And it can be positive or negative, and so we square them for that data point. That is the residual. So each data point in your 30 rows of data has a residual with it. What is it? It's the difference between the best fit line, which we sometimes call the Y hat. In this case, you can call it the Q hat line. So that's the predicted value from the regression using the best fit versus the actual real data point. And then that's how the computer did that. So part A, the coefficient is the best guess. We don't know the true relationship, right? We'll never know the true relationship. We can only get more and more confident that our variables are explaining something that we put into it. How much? We look to the R squared. As we start to get more and more confident, the R squared will climb. If there was an R squared of 90%, then that means it would fit the data really well. And we can be pretty confident that this predicted line is getting really, really close to predicting a pretty good relationship of the variables. Okay, so now part B, the standard error of the coefficient, the SEC, measures how much wiggle room there is in that coefficient. The standard error labeled in cell C16. Do not confuse the standard error of the coefficient with the standard error of the estimate with A7. Both are labeled standard error. So let's go ahead and find those on the sheet. C16. So C16 is the standard error of the coefficient. So notice that the coefficient is here and the standard error is here. By the way, I kind of jumped. Notice that we threw in all the variables here. So we went yesterday, I left you off with, we just did price of the slice and the price of the soft drink. And so now we do the same thing we did, just take that whole row of data and run the regression, and this is what the output would be. So we can do that maybe later on our own with some of the exercises if we want, but I think you guys are pretty comfortable from yesterday. Dakota, I hope you carefully went through things yesterday because you missed an important one.
Yeah, I haven't finished watching it yet, but I'm watching the back half of it.
So we know just from the way the output is generated from Excel that this standard error is the standard error of the coefficient because it's right next to it. Okay? So that's what he's saying about don't confuse that with A7. A7 is the standard error of the estimate. That is of the whole ball of wax. So this one here has, like the R squared now has gone up to 88%. So it says 88% of the variation in the data is being captured by these variables. And so that standard error is related to the overall regression rather than just the coefficient. Okay, so T-statistics is measuring this wiggle room. So T-statistics are calculated as the coefficient divided by the standard error of the coefficient. So just to give you a little bit of intuition on this, this isn't a perfect explanation, but if we did a normal probability distribution and notice that our price of the slice, what was this number before when we did it with just that variable only yesterday? What was this coefficient equal to? You can look back on your old sheets if you want. Negative 0.08. So this has now changed to 0.01. We'll talk about that more later here on what might be going on. But that is the coefficient. So I'm just going to use that one for now, 0.01. is the best guess, the most probable guess, right? So with the probability distribution, we're measuring, this is probability over here. It says that that estimate is most likely 0.01, but it could be wrong. So when he talks about wiggle room, the computer is saying if these data points were really scattered, then I might not be as confident about that coefficient. And so the probability distribution may look like this. Which one are you more confident about? The one associated with the blue curve or the red curve? Which one are you more confident that this is a good number? The blue curve. So the blue curve says that it's 0.01. I'm pretty sure it's 0.01, and so does the red curve. But what the red curve is saying is that, well, it could be 0.01, but it could be this or this. The blue curve is saying it could be this or this, right? It falls into this narrower range. So I'm more confident about the one associated with the blue curve as opposed to the red curve. That's what the standard error of the coefficient is starting to measure for us with the probability distribution. So the formula for it is simply that divided by the standard error of the coefficient, and it gives you what's called a t-statistic, which is just a kind of a statistical anomaly that'll show in a little bit here. But we've got some nice rules of thumb then to say whether it's significant. All right, any questions so far? So reported regression, now I'm on D. Regressions typically list coefficients in either SEC or T, but not both. So when you guys look at papers in journal articles, so when you guys start looking at professional journals here, it will show the estimate and the coefficient, and then it'll show here, it's showing the t-statistic, 3.52. And so what the author's saying is that it'll usually give you one or the other. Sometimes they give you the standard error of the coefficient in a journal article, but usually not both, because you can calculate the t-statistic using this equation. So just as a way of reporting it to other professional economists or the reader, they'll just do one or the other. Okay? All right, so E, given the equation that links the three values, any two determines the third. So note K9 through K14, let's find K9 through 14. K9 through 14 is right here. Right? So we got the coefficients and the t-statistics. Are the same values as C17 through D22. C17 through D22. C17 through D22 over here. But the ones in K9 through 14 are based on equations. So they basically did that equation in here. So check it out. If you take any one of these, the author used the equation to calculate it. Okay, and he's just showing that it generates the same number. All right, questions there? All right, here's the big thing that you need to have memorized. This is the most important part of this. So the rule of thumb is that if the absolute value of the t is larger than 2, then the variable is a significant predictor of the dependent variable. This rule works when samples are large. A more accurate statement requires knowing the critical t value based on a t table. A variable is significant if the absolute value of the t is greater than the critical t. T crit is the kind of shorthand for t critical, is based on the regression's degrees of freedom, df, and the significance level. DF, degrees of freedom, are n minus k minus 1, where n is the number of observations. There was 30 with the college, 30 college observations. K is the number of independent variables. There's 5, and 1 is for the intercept. The significance level is typically set at 5% with a two-tailed test. This leads to a 95% t-critical of 2. By comparing T to T-crit, we see that P-slice P, soft drink, and residential are significant predictors of quantity of slices, but tuition and urban are not. All right, so there's a barrel of fish hooks. What the hell does that all mean? I'm not sure where you guys were all at with your previous statistical knowledge, so how many of you remember something like that in a previous class? How many of you understood what that just said, pretty much? Maybe kind of like this.
But isn't it a negative number?
Negative, it's the absolute value. So the absolute value, it takes a negative number, makes it positive. A positive number stays positive. All right, so here is where some of this is coming from. So in your textbook, at the very back, page 575, I don't know if any of you have your book. Looks like Luke, you got it here. 575 if you have your book with you. So table A4 shows the critical values for the t distribution. So you've got one tail and two tail. And so it's a 5% level of significance. So here's what's going on. Back to my example here. I feel pretty confident about 0.01 if it lies within 95% of the normal distribution. So a combination of whether it's the red line or whether it's the blue line. If it's the blue line, I feel more confident that 95% of those observations are going to fall within 2 standard deviations, which we haven't talked about standard deviation, but that's one of the measurements. And you guys, just so you know, we're kind of running the line of we're not making this a full-blown statistics class. In theory, you had some of this in the past, but I want to give you a little bit of the background so you got the intuition rather than just reading off the numbers. So kind of ask questions as we go, but that's the idea of it here, that we're in this zone. And the farther the zone is, the more confident we feel. Well, what is that zone? Well, that zone is determined by like how many observations you had, right? So imagine if we did a survey with 10 people. Is 10 college students representative of the whole student body? It's hard to say. We get more and more confident if instead of 10, we interviewed 30 people. We get even more confident if we did 50 or 60. If we did 100, if we did 300. Now, if we did 800, what did we just do, at least here at Ottawa, if we did a survey of 800? That's the whole population, right? Which we might not have the resources to do so with, right? So how do we know what's the proper number of people to survey to be representative of the school? Well, it has to be a random sample, right? We don't want to just go, oh, let's just go to the football team. It'll be easy. Coach K will let me in there, and I'll get all my sample from the football team. Well, what would be some problems with that if we got all 30 from the football team that you can think of here?
Variation.
No variation. What kind of variation?
All dudes.
It's all dudes for starters, right? So we got all dudes, we got all football dudes, whatever that means, and so it's not representative of the whole population, right? So we'd have to have random samples. So assuming that somehow the sample is random and representative, the general rule of thumb is to get at least 30 observations. It's kind of a statistical anomaly that once you get up to 30, you've reached this 2, this magic number of 2 right here, and even at 60 with the two-tail distribution and the one-tail over here. So that the one-tail, two-tail stuff, we'll talk about a little bit later, but it's whether you believe you have equal probability of getting something on the right and something to the left. So if you're only possible for it to be a positive number or to be this side of the estimate, that's where the bias lies, then it's a one-tailed test. And we'll talk about that a little bit later, but that's the difference. That's what's going on with this two-tail, one-tail. It comes from the probability distribution. Okay, so anyway, here's the magic number of 2 that even as we get down to 20, notice that it's 2.093, 2.086. At 30, we get down to 2.04. So general rule of thumb is if your number is bigger than 2, then you're in that 95% world. So that's what is nice about this rule of thumb, is now when we come back to here, the normal probability distribution, the shape of it is determined by the number of observations, the degrees of freedom technically. So, and then as long as you have a number that's greater than 2, then you can be confident about that number. Okay, let me pause there for a second. Questions? I feel like I threw a lot at you now.
Is the t-stat the only value that's an absolute value, or anything else like coefficient is possible to be negative?
So the t-stat, if you have a negative coefficient, let me, so if you have a negative coefficient, where's the, so here's the coefficients, right? You're going to have a negative t-stat. Remember the formula, it's just this number divided by this number. And so it has to be negative. And same thing here, if the coefficient is positive, it's a positive number divided by a positive number gives you a positive number. So it's going to always work out that way. So with the t-distribute, or with the critical t, we take the absolute value just so that we don't have to think about whether it's negative or positive, because it's just going to be significant. The sign, remember, is the relationship between the variable and the dependent variable, the independent variable and the dependent variable. Price goes up, quantity goes down. Price goes down, quantity goes up. So a negative relationship is where that sign is coming from. In terms of its significance of whether we think it's greater than or significantly different from 0, we're using the t-statistic, so we can just ignore the sign. It doesn't matter for significance. Does that help? Any other questions on that?
That's what I'm saying. You interpret again, you say that decrease of an increase of 1 unit quantity would be price of by 0.09.
A 1 unit increase in price will lead to a 0.09 decrease in quantity of slices. Remember, this is the effect on the quantity of slices. If we look here, this is negative 0.09. So if I plus 1 here on the price of the slice, the impact at the margin on quantity of slices is going down by 0.09 of a slice. That's all separate from this t-statistic business. Okay. But that's where I'm going to go next to with what he said. So he said, by comparing the T to the critical T, we see that the slice, soft drink, and residential are significant predictors of quantity of slices, but tuition and urban are not. Why? Well, this would say a 1 unit increase in the price of tuition would lead to a 0.05 increase in sales of quantities, correct? It would be if we had faith in this number, but we don't. That number is looking more like the red. It's like, oh, this is really lousy. The computer gave us, what is it, 0.05. The computer gave us 0.05, but shoot, it could be way over here or way over here. In fact, 0 is included with this. And if 0 is included, what's the interpretation of that? Has a high likelihood of potentially being 0. What does that tell you about tuition then? If it was truly 0, let me do a plus B3 tuition. If B3 equals 0, what would be your interpretation of the effective tuition? Nothing. Tuition goes up by $10,000, leads to 0 pizzas going up, right? So we have to be comfortable that this estimate is far enough away from 0, or the probability distribution is more like the blue one, so that 0 is not included. If 0 is included in the 95% likelihood, then that coefficient is BS. If this coefficient is BS, 0.05 is equal to 0. It might as well be 0. So that's what we mean by significance, is that we have to have the t-stat be over 2 for us to be comfortable that 0.05 is a good number. So we say that it's not significant. Okay, same thing here with the t-stat on urban, whether we're in an urban area. So then the research question would be, does it matter when a university is in an urban area that you're going to sell more pizza? Does that make a difference? My research shows that, nope, it doesn't matter. That's the answer to your question. It doesn't matter that it's going to be, because it came up with 0.74, but 0.74 was not significant. It might be 0. I don't have enough data. I don't have enough information to claim that tuition or that urban area matters or not. And that would be what you'd report on your final capstone paper, by the way, too. I don't have enough evidence to say that tuition matters. I thought that it would, but maybe it doesn't, according to my research, my data that I have. Okay, questions there? All right. So then this last thing, K, note that the critical values for the 0.05 two-tailed test are close to 2, especially for large values of degrees of freedom. That was kind of from the table, I guess, that we just did. All right. Let's see. I think this is a good spot to bring up hypothesis testing before we move on to the next one. So if you have your book, you can turn to, I'm going to show it on the overhead too, but chapter 5. Page, here we go. Page 121. Okay, so how many of you are familiar if I say the statistic method? What am I talking about? Statistic method. Okay, yeah, so that'd be one way to test it, right? So how, like when somebody says, I believe in science, right? We've had all this crap with COVID and everything else. Is like, well, we got to believe the science. What does the science mean related to COVID? When somebody says, let's trust the science, what the hell did they do? Put a mask on. No. Experiments, good. Why? Drill down on that. That's exactly right.
Because they produce stats.
Okay, that do what?
Prove a point longer, right?
Yeah. So the wear a mask would be the hypothesis, right? Masks save lives, or masks don't save lives. Now, we can talk about our gut feeling all day long that, oh, well, come on, it's obvious if I'm not spitting all over you that we're not going to have COVID. Oh, really? Are you sure? Are there other factors of whether people properly wear a mask or whether they do, you know, whatever. So what do? We go to the world and we test that hypothesis. So if we're looking at setting this up scientifically, let me write it over here. Yes, we have the null and the alternative hypothesis. So the null hypothesis, which sometimes we say HO, The null hypothesis is that B1 equals 0. And this is where mask. Do masks work? Well, the null hypothesis is that it doesn't work. And that's just the way you set it up scientifically, by the way. So you don't lead in with kind of trying to confirm your bias. So that's what we're testing. And so we're going to start off theoretically saying masks don't work as one side of the theory, right? The null, the status quo. Have we worn masks in the past? No. So let's start off with that masks don't work as a hypothesis. And then our other hypothesis is that beta 1 does not equal 0. Masks have an effect. That's it. Then we're going to do this junk, and we're going to test. Now, what's interesting here is if beta 1 turns out to be less than 0, so note here, there's kind of two things that could go on. Beta 1 less than 0, beta 1 greater than 0. So which one says that masks save lives? B1 greater than 0, right? More mask wearing leads to more lives saved if our dependent variable is lives saved. So masks greater than 0, masks have a positive effect. Masks save lives. And then what does this one say?
That masks actually are hurting.
Masks are hurting, yeah, masks kill. So our theory allows the data to tell us what's going on, not some expert in the field that has a gut feeling. That expert who does this study has the data available for the world to do the same test that that expert did. So if the expert is being deceptive, the scientific method, part of the principles of the scientific method is that we have the ability for other experts to run the exact same data and they come up with the same results, verifiable, right? So part of the scientific method is that your results are verifiable. And so when you send off your research to an academic source, the editors, or the we call them referees for the journal, are other experts that can run your data or interpret it themselves. They can rerun it. So the results are verifiable. So now notice we are relying on the scientific method. Is that a human being, the scientific method? No, we're not relying on human beings anymore. For the ultimate conclusion, right? The human being is using the tool of the scientific method to get insights about what harebrained theory of mask wearing, whether that works or not. I'm just using harebrained because all the confusion and fights that we have about masks is a testable hypothesis. That's using science to determine whether masks were effective. That's the scientific method. That's what you guys are charged to do with your capstone, is to use the scientific method to either show that the null hypothesis seems to be what your data indicates, or that the alternative hypothesis is true, and that something is significant. Okay, questions or comments there? So here I put up on the screen, just to kind of motivate this a little bit more. So hypothesis 1, the price of pizza, x1, is an inverse determinant of the quantity of pizza demanded. The sign of the coefficient is expected to be negative. So one test would be that we specifically want that to be negative, right? We want that we're looking for a negative sign. Hypothesis 2, assuming tuition to be a proxy for income. What do we mean by proxy? Tuition as a proxy for income. Yeah, so it's used as kind of a substitute, right? So in an ideal world, we'd have the household income for the college students, right? The idea is that rich kids eat more pizza than poor kids. And so, is that true? Is it not? Well, oh darn, I don't have income data. You guys might find this in your study. Of course, you go back to principles class. Remember the shifters of demand, price of the resource. I'm sorry, that's not the shifter, but I should say determinants of demand. The price of the good itself, the price of substitutes or complements, income, taster preferences, expectations, all of that stuff are the basic determinants of the dependent variable, the number of slices we're going to buy. So we don't have income, so we're going to try tuition thinking that higher tuition schools, who goes to higher tuition schools? Rich kids or poor kids? Rich kids, in general, but it's just a proxy. We don't know, it might not be a very good proxy or not. So therefore, we hypothesize that tuition is a determinant, but we cannot say beforehand whether it's inverse or direct, positive or negative. The sign of the coefficient could be either positive or negative. Hypothesis 3, the price of a soft drink is an inverse determinant to the demand for pizza. So it's expected to be negative. Location in an urban setting, expected to be an inverse determinant of demand. So inverse determinant means, what's the sign? Negative. So urban means less, and pizza demand, hypothesis 5, is expected to be lower at residential colleges. All right, so now when we do this, we're going to turn to the regression results for all of that stuff. I'll let you guys kind of read that, but I wanted to jump down to so by the way, this is saying about the magnitudes, kind of what we just walked through with the t-stats. Maybe on the other side. Oh, here we go. Oh, I didn't have a post-it note for you guys. Yeah, I had that. All right, here I guess is, I'm missing, there's something in here about, talks about the two-tailed test. Here it is. Okay. Let me jump down to here first since I brought it up before. So turning to the table in A4, the critical value at the 5% level of significance is 1.7 using a one-tailed test and 2.064 for a two-tailed test. The t-value computed for a particular estimate of coefficient is greater than 1.7. We can say that the estimate is significant at the 5% level using a one-tailed test. If greater than 2, the same can be said for a two-tailed test. A simple, useful way to handle the critical level of the use is the rule of 2. This means that the absolute value 2 is coefficient of pizza. All right, so in the t-test that we just did with the two-tail and the one-tail, so price of pizza, soft drinks, and residential because they're big. The other two variables, tuition, are not because the absolute values of t-stats are less than 2. Okay, anyway, I was trying to bring up the two-tail test, one-tail test is this, where we're saying the sign is to be negative. If that's your test, then you have to beat the 2.06 rather than the 1.7, right? So you need more if you're doing a one-tail versus a two-tail. Usually you're doing a two-tail, but it does depend on your hypothesis. All right, so again, this is what we just went over on this Excel spreadsheet, degrees of freedom. And then this is kind of the language that you use, reject the null, not accept the alternative. So if you get a result that is that your coefficient is significant, then we're rejecting the null hypothesis. We're not saying we're correct. I think this is good because you're not trying to prove. So watch with your capstone papers that you don't say, this proves that masks don't kill people. That's not what you're saying. You don't want to be that strong. We're not proving anything. Why? Because it's dependent on your data, how it was collected, you know, the time of the year. We're not omniscient. We don't have perfect information that you proved that the world works this way. However, you can be pretty significant that according to your data, you're going to reject the null that it's 0. My data suggests that it is significant. Okay. Questions? I feel like I'm getting way too worked up on this. All right, back to here. All right, number 2 is the mistake-free way. Regression is to create output and estimate in pieces. All right, so suppose you want to estimate demand at a non-residential college in an urban area, given average prices of $1.50 and the price of a soft drink of $1, where tuition is $20,000. A27 is one way, but H16 through I23 is easier to do, and it is less likely to lead to errors. Or go ahead and identify those cells. So A27 is one way. If you highlight that, look at what showed up in the equation bar. What is in the equation bar? A lot of malarkey. Well, track down that malarkey.
Innocent concept is like plus quantifier 150 plus your
And what's the 150? Let me pause there.
price.
It's the price, right? So it's in pennies. So 150 is in pennies, so we get rid of the decimal place over. So what is it? It is taking the estimates. What's B17? The intercept. So we're just using the equation right here. B17, we're using those coefficients. We're plugging it in here. And then we're saying, oh, $1.50. And the price of a soft drink is $1. So that's what that equation's doing, is if you double click it, then you'll get your highlights. So it's showing those numbers plugged in times the 150 they just have in as a number. So E18 times it plus this, they're just plugging and chugging that equation. Okay, so now he says, yeah.
Is it 20,000 tuition only 20?
Not about to ask.
Just because it's measured in thousands. So with your data and with other things, similar to what we did here with the 150, we changed it into pennies. When they did their data, you can just change it from thousands to pennies. So, and by the way, I think there might be another exercise where we do this, but if you instead use 20,000, what's going to happen to this coefficient? It'll shoot up. Yeah, it's going to adjust. So it doesn't matter what units you use as long as you're consistent. So if tuition has a 0.05, and it's 20,000, then this is going to be it's going to shoot over the number of thousands, right? So it doesn't matter if you use 20 or 20,000, and of course, in your data, it might have been 20,567 would be 20.567 on your data list. So that's going back to your main data.
And we do the process of 5,000.
So check it out here, just to be crystal clear on this, because this is a good question. Tuition is measured in thousands. So this is a college. College number 2 has tuition of $26,360. Right? That's all they did. So then we're just plugging it in the same way, trying to make a prediction using that. Okay, anything else there? All right, let me see where we at here. Is this where we're on? Yeah, okay. All right, so now A27 is one way, but H16 through I23 is easier to do and less likely to lead to errors. So H16 through I23, H16 through I23 So look at what he did here. What did he do? What is he saying with H16 through I23?
Taking the coefficient and multiplying it by the values.
Yeah. So just creating your own equation in pieces is what he's saying. So instead of doing one big equation, he's saying you're likely to screw this up. Look at that equation, right? You guys said it's a big mess. The 150 times this one, you're right, a big equation. It's safer to do this way, where now you've got the pieces. So you've got the $1.50 and the 20,000, and this is the intercept, so the value was 1. So this thing is just this number times this number, this number times this number, add them all up, and there's your prediction at the end is this, where we're just summing them up together. So all we did is that same equation, but you did it in pieces. All right, questions there? Just trying to give you a little heads up that might be a little bit easier to do it that way. All right, this will sum the pieces together. An additional benefit of doing it this way is you can easily change the values and see what happens to the estimated demand. So if you wonder what happens with $1, so we were kind of doing this before, with all else remaining the same, simply enter 100 with the new results 12.2. To do this in a manner similar to 827 would require a whole new equation. So if we come up here, now we can play some games and say, what happens if we have a sale to 120? Let's take 30 cents off, right? So you guys go ahead and play around, take 20 cents off, and we just sold 10 more slices, right? Or not 10 more, so we went up to 10 from 7, so we sold three slices. So that's kind of nice to play around with a little bit with demand estimation. We sold 2.5 more slices when we dropped the price 30 cents. Okay, questions on that? All right. Confidence intervals. Now this will start to come together a little bit better with the background that we did. So regression provides the best guess estimates of both coefficients and predicted values. A confidence interval provides a range of values surrounding the best guess, so you're confident that the actual value is contained within. Statisticians and economists typically allow a 5% error rate. So they talk in terms of a 95% confidence. So on a two-tailed distribution, with 5% error, if it's two-tail, that represents a 2.5% error. And this represents a 2.5% error. Combined together gives you 5% on a two-tailed test. So so you guys see this then? We're 95% confident that that coefficient falls within that range. All right. So look at this formula. The confidence interval is just the best guess, which is the coefficient number, plus or minus the t-critical times the standard error. So that's giving us our range going back to the coefficient. Okay, so did you guys do this little exercise up here? What's LB? Lower bound and upper bound. Good. So if we go to on D here, the confidence interval and estimates such as 7.53 in I23.
That was the best guess.
Yeah, that was our best guess for the dependent variable. And then the standard error for the estimate is from B7. Remember, this is kind of your standard error for the overall regression. So it's your dependent variable that's the standard error. So that's B7. And then the critical T is usually 2. So you guys might remember from this stuff, you're within 2 standard deviations of the mean. That's where the 2 actually comes from, is from this critical T. So you're approximately 2 standard deviations from it means you're 95% confident of it. So that's kind of the rule of thumb and where it's coming from. So taking the critical t 2 times 2 standard deviations, our best guess is plus or minus 2 standard deviations, because this is 2 times the standard error, 2 standard deviations from it, and that gives us our 95% confidence interval. So we're 95% confident that our 7.5 estimate is somewhere between 5.3 and 9.7. Okay. So let's see, the slope on elasticity, and check 4. So here he just kind of brings in the elasticity formula. So using the point estimate, price of the slice divided by the quantity of slice, and then that's the slope term. We can do confidence intervals on the price elasticity too. All right. Okay, I want to. What is the confidence interval on urban? Or let's do tuition, since we did tuition before. A 95% confident upper bound, lower bound. What is that saying about tuition? Why tuition is kind of potentially a problem? What does the confidence interval cover? What's in between there, lurking in the dark? 0. Right? So if my 95% confidence interval includes 0, then it's garbage. Because we don't want it to include 0, because if it happens to potentially have a probability of being 0, then the coefficient is garbage. Right? We don't have enough confidence in it, given the data that we have. So same thing here with urban. The confidence interval covers 0 within the interval. So when we're confident about it, then we don't include 0 on the 95% interval. So that's another way to think about that. 95%.
Isn't that strange since your p-value is pretty close to 0.05? And p-value makes the two relationships.
Yeah, so I mean, for the coefficients, the p-value, we usually just kind of don't talk about. So you might remember more from George's class than I can expound on. But we don't really, there's a few places where we talk about the p-value, but all of the focus is on the t in terms of significance. What do you remember about it, JC?
I just remember the close to 0.05 relationship between p-values. That's what we focus on, p-values, so p or
relationship between the variables?
Yeah, between the independent and dependent variable. For example, p slice will have the tuition will have a statistical relevance to tuition at the p-value is 0.09.
Yeah, and so the p-values also, let me go back here to the tables.
Maybe not use it in this one.
Yeah, no, it's a good question. I won't spend too much time on it, but I want to see if the p-value is in here. Yeah, we really just do the t, but it's a, yeah, they don't have it in here. But there's also the F distribution is kind of similar, but again, we're not going to use it for our purposes here, so we don't want to cloud up things. But there's the F distribution, and then the p-value is another formula that's related to it, and I honestly can't remember off the top of my head. I was hoping you could educate me on it, but if you're good, then I'm good.
My paper for this final paper, I did the difference between the pay ratio, PE ratio compared to stock price. The PE ratio was pretty close to 0.05 or less.
Yeah, it is something to do with the overall, but, okay, let's move on. Do a little side work on that one. Top of my head, it's not even in the book, so it's just one of those that they kick out. So understanding the difference between magnitude and significance. All right, so this one probably easiest to read out. Students who are just learning regression often conflate magnitude and significance. What does it mean to conflate? Kind of mix up and confuse, put the two together as if they're one, is the idea of conflating two things. So magnitude is the size of the coefficient of the distance from 0. Significance is how much faith you have in it. So magnitude and significance are definitely two things. Make sure you keep them different. The coefficient for urban is 8 to 9 times the magnitude of the price of slice or soft drink. But urban's not statistically significant, while price of slice are both. So if we come up here and we think about the magnitude is 0.74 versus 0.09. So the size of the coefficient seems big, but of course remember also that that's a dummy variable. It's either a 1 or a 0. So if you're urban, then that's going to lead you to buy a lot less pizza, 0.74, besides just the 1 unit price. Of course, the 1 unit price here, remember, is just a penny. So the size of the coefficient versus the significance. So this one includes 0 again. So it really, we treat it as 0. So it's not significant, even though the magnitude is 7 times higher than what the price of the slice is. Does that make sense? Yeah. So just make sure you keep those two things separate. All right. Well, that was a pretty good bump in the woods here. So let's see that. Couple things then to wrap up today so that we can get you guys set for doing the work here. That was the thing that took the longest time. So the dummy variable with this, here they ran a regression where they just put residential in. Is it significant? Is residential significant? Looking at this data here, they only ran the price of the slice and the dummy variable residential. Is it significant?
Yes.
T-stat is 4, which is greater than 2, which means this is greater than 0. We can kind of now look at the upper bound, lower bound for the interval, and we kind of see that it doesn't include 0. So that is significant. So what does that mean? With a dummy variable, you're essentially adding in a lump sum term to the intercept. And so conceptually what that says is that the computer is picking up 2 fitted lines, depending on whether a college is actually in a residential area or not in a residential area. And the computer's finding that that result is significant. And so with it being a -3 in a residential area, it's like a shifter down. So we were at 20 and now we're at 17 roughly. And so that is what a dummy variable is doing if it's significant. So it kind of says, like, if you're making a prediction, you're saying, oh, well, if you're in a residential area, then when I make my prediction, this is what I'm doing with you, right? But if you're not in a residential area, then you're on this line, if I was making a prediction. So the 0, 1 is going to make a difference on whether you're on the upper one or the lower one. Okay, so he talks about that here with dummy variables. I'm going to let you guys do this on your own. I'm just pointing out a couple things here. And then 3B is a little bit more detail on how you structure it. So there's the urban variable, there's the residential variable. So both dummy variables in the above regression were based on two categories. This need not be the case. The partition of the data is a categorization scheme with each observation put one way and only one category. For example, the location could have been a three-way partition of urban, rural spectrum. In this event, two dummy variables would be created. There are three possibilities. So urban, rural, urban, suburban, rural, suburban. The baseline scenario for trying to test suburban versus rural versus urban. Or generally, if there's k possible options, then k minus 1 dummy variables would be needed to create a partition. So you can have multiple categories. You might find this in one of your papers of like, this is saying 3 categories. But your baseline then is you're only going to have 2 variables. You're like, oh, but Russ, I want to test, you know, A, B, and C. And I'm like, you are testing A, B, and C with just the full run. So one of them is going to suck out one of the options, suburban in this case, and the other option is going to suck out the other one. So you'd only have 2 dummy variables needed for your 3 cases that you're doing. Okay? Again, just kind of giving you a little introduction. You can doodle that through on your own. And this is the worksheet that he works through different demand for pizza slices. So this is kind of cool. He's going to bring you through what's happening to the R squared with each run and showing the results. So now that you guys got your arms around adding a variable, what happens when we add a variable? So it looks like a lot to look at, but again, hopefully you're getting a little more comfortable as we work through it. And then the R squared. So a little more detail on what that means. And then there's an adjusted R squared, which is this one, adjusted R squared versus R squared. It takes into account that if you keep adding variables, R squared goes up, but it may not be adding anything. And that he's going to walk you through that little exercise. And then you guys will be pretty well set here. These were just tables from the book with the data. All right, that should be enough to blow your minds. Any questions?